Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d hybridization with one lone pair and two pi bonds in the main structure. So for this concept, I'm taking the example of xenon dioxy difluoride. So our today's example is xenon dioxy difluoride, that's xeO2 F2. Before proceeding towards the hybridization, let's make the Lewis structure of xeO2 F2 first. So that's our Xe. That's my oxygen, the second oxygen, and that's my fluorine over here, and that's my second fluorine over here. Now, what's the atomic number of xenon? As we all know, xenon is a member of group number 18. That's the noble gases. That means xenon is going to have 8 electrons in its valence shell. So let's mark 8 electrons around xenon. There's first electron, the second electron, third electron, fourth electron, fifth electron, sixth electron, and that's the seventh electron, and that's the eighth electron. Now let's talk about the oxygen. What's the atomic number of oxygen? That's 8. So its configuration will be 2, 6. That means oxygen is having 6 electrons in its valence shell. So let's mark 6 electrons around both the oxygen atom in Lewis structure. So I'm talking about the first oxygen first. That's the first electron, second, third, fourth, fifth, and the sixth. Now let's come to the second oxygen. That's the first electron, second, third, fourth, fifth, and the sixth. Now let's talk about the fluorine. The atomic number of fluorine is 9. So its configuration will be 2, 7. That means fluorine is going to have 7 electrons in its valence shell. So let's mark 7 electrons around both the fluorines. So that's the first electron, second electron, third, fourth, fifth, sixth, and the seventh. Let's come to the second fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now what's going to happen? Now the first oxygen is going to form 2 bonds, that's double bonds with xenon. The second oxygen is also going to form 2 bonds with xenon. So that's the first bond, second bond. Now fluorine is going to make 1 bond with xenon, and the another fluorine is going to make 1 bond with xenon. Now let's count the number of valence electrons for the first oxygen after the formation of 2 bonds with xenon. So I'm counting the electrons. The first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means first oxygen has attained 8 electrons after the formation of 2 bonds with xenon. Now let's count the number of valence electrons for the second oxygen after the formation of 2 bonds with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means second oxygen has also attained octet, that is 8 electrons in its outermost shell after the formation of 2 bonds with xenon. Now let's count the number of valence electrons for the first fluorine after the formation of 1 bond with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So here also fluorine has attained octet, that is 8 electrons after the formation of 1 bond with xenon. Now let's count the number of valence electrons for second fluorine after the formation of 1 bond with xenon. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means second fluorine has also attained 8 electrons in its outermost shell after the formation of one bond with xenon. Now, let's count the number of valence electron for xenon after the formation of 2-2 bonds with both oxygens and 1-1 bond with both fluorines. So let's count it. So that's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, eighth electron, ninth electron, 10th, 11th, 12th, 13th, and the 14th. That means xenon has attained 14 electrons in its valence shell after the formation of 2-2 bonds with both the oxygens and 1-1 bond with both the fluorines. So here is the case of expansion of octet. That is, xenon has attained more than 8 electrons, that is 14 electrons in its valence shell after the formation of bonds with 2 oxygen and 1 fluorine. Why so? Why xenon is capable so? Because xenon is having vacant orbitals in its d subshell. That's why xenon is eligible to expand its octet. So now let's talk about the hybridization. Firstly, here in case of XeO2F2, here our central atom is xenon, because xenon is forming maximum number of bonds, that is 6 bonds. So now let's talk about xenon. The xenon is a member of group number 18. Let's write the group number 18. Helium, neon, argon, krypton, xenon, radon, oganesson. Here, that's our period number 1, 2, 3, 4, 5, 6, and the 7. So xenon is the member of period number 5. Now group number 18 has a general electronic configuration of NH2NP6. So we got the configuration of xenon to be 5s2 5p6. So let's take the electronic configuration of xenon now. That's our xenon with the electronic configuration of 5s2 5p6, and xenon is also having d subshell in the fifth shell with 0 electron, or we can say xenon is having vacant d orbitals or the d subshell. So let's make the orbital diagram in the form of boxes for the xenon. As s subshell has only one orbital, so that's our 5s. The p subshell has 3 degenerate orbitals. The orbitals which have equal energies are called degenerate orbitals, and in case of p subshell we always have 3 degenerate orbitals. Now let's come to the 5d. In d subshell we have 5 degenerate orbitals with equal energies. So that's our 5d. So now let's fill the electrons according to the electronic configuration. The 5s is having 2 electrons. So let's fill 2 electrons in the 1 orbital of 5s. That's our first electron with a spin of +1/2. That's the second electron with a spin of -1/2. Now let's come to the 5p. The 5p is having 6 electrons. So let's fill 6 electrons in degenerate 3 orbitals of 5p according to the Hund's rule. Hund's rule states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each. After that pairing will start. According to that, the first electron will be in the first orbital, second electron will occupy second orbital, third electron will occupy third orbital. Now pairing will start. Fourth electron will come in the first orbital with a spin of -1/2, and we got the first pair in the first orbital of 5p. Now fifth electron will come in the second orbital again, and the sixth electron will come in the third orbital with a spin of -1/2. So in all the 3 orbitals we got the pairs of electron, that is 2 electrons per orbital. And this is our ground state. That's our ground state of electronic configuration. Now let's come to the Lewis structure. Here, how many bonds are formed by xenon? My question is, how many bonds are formed by xenon? Here in total, xenon is forming 6 covalent bonds. Here xenon is forming total of 6 covalent bonds. So that means in the electronic configuration of xenon, xenon must have 6 orbitals containing 1 electron each, so that xenon can overlap with the atomic orbitals of the other atoms containing 1 electron for the formation of the covalent bond. I'm repeating it again. If xenon has to form the 6 covalent bonds, then xenon must have 6 atomic orbitals containing 1 electron each. Only then xenon will be eligible for the formation of 6 covalent bonds with the other atoms. So for that, let's excite the electrons from 5p to 5d. So that's our first electron, which is going to get excited from 5s to the from 5p to the 5d. That's our second electron, which is going to excite from 5p to the 5d. And that's our third electron, which will be excited from 5p to the 5d. So here 3 electrons are getting excited or promoted from the 5p orbitals to the 5d orbitals. So let's make the new electronic configuration. That's the excited state. That's our 5s. That's the 3 orbitals of 5p. And that's the 5 degenerate orbitals of the 5d. So now let's fill the electrons. The 5s is having 2 electrons. These are the 2 electrons. Now 5p is left with 3 electrons only, the first, second and the third, and the 3 electrons have jumped or excited from 5p to 5d. So that's the first excited electron, second excited electron and the third excited electron. So that's our excited state. And here you can count the atomic orbitals of xenon which are having 1 electron, and they are 6 in number. The 3 orbitals from 5p and 3 orbitals from 5d, by which xenon is eligible for overlapping with the 6 atomic orbitals of the other atoms for the formation of the covalent bond, for the formation of total of 6 covalent bond. I'm repeating it again. If xenon has to form 6 covalent bonds, then xenon must have 6 atomic orbitals containing 1 electron each, so that xenon can overlap, so that 6 orbitals containing 1 electron of xenon can overlap with the atomic orbitals of oxygen and fluorine containing 1 electron for the formation of total of 6 covalent bonds. Now let's come back to the Lewis structure. Here oxygen is forming 2 bonds with xenon. Whenever there is a formation of double bond or the 2 bonds, then out of that 1 bond, the 1 bond is always sigma and the another one is pi. Let's come to the second oxygen. It's also forming the double bond. Then out of that 1 bond, one will be sigma, another will be the pi. If there is a single bond, then that's always sigma. So fluorine will form the sigma bond with xenon, and the another fluorine will form the again sigma bond with xenon. So out of 6 covalent bonds, how many we are having sigma bonds? We are having 4 sigma bonds and we are having 2 pi bonds. So now we are doing the topic of hybridization. I'm marking one point, and that point is hybrid orbitals only forms sigma bonds but not the pi bonds. So in this orbital diagram, our next topic is the intermixing of atomic orbitals. So during the intermixing of atomic orbitals, we have to consider only that atomic orbitals which are going to form the sigma bonds. Here in Lewis structure, we are having total of 4 sigma bonds. So in hybridization, we have to consider the 4 atomic orbitals which are containing 1 electron each, not all the 6 atomic orbitals, because out of 6 atomic orbitals, 2 will form the pi bond and another 4 orbitals containing 1 electron will form the sigma bonds. So let's take the hybridization. In hybridization, firstly, we have to take the atomic orbitals which are having electrons. Now 5s orbital is having 2 electrons, so we have to consider that orbital in the hybridization. In each and every hybridization, s orbital will always be there. So I'm taking one s orbital containing 2 electrons, the 3 orbitals from 5p containing 3 electrons, and 1 orbital from 5d containing 1 electron. So in hybridization, I have taken one s orbital, 3 p orbitals, and 1 d orbital. So we have taken total of 5 atomic orbitals, out of which one is having the lone pair of electron, that's 5s, and remaining 4 orbitals, the 3 from p and the 1 from d, are having 1 electron. So xenon will form 4 sigma bonds, because in hybridization we will get the hybrid orbitals, and hybrid orbitals only form the sigma bonds, not the pi bonds. So here the intermixing of 5 atomic orbitals will take place, 1s, 3p and the 1d. So that's our intermixing process. And this intermixing of atomic orbitals is called hybridization. Now, we have intermixed total of 5 atomic orbitals. So we are going to have 5 new hybrid orbitals. The number of atomic orbital mixing and the number of hybrid orbitals formed are always equal. So we are going to have 5 new hybrid orbitals and they will have the equal energies. So we can also write come degenerate orbitals. So I'm making 5 new hybrid come degenerate orbitals. Now, what will be the name of the hybrid orbitals? As it's a mixture of 1s, 3p and a 1d. So this hybrid orbital will be called as sp3d hybrid orbital. The second one is also sp3d hybrid orbital. Third one is also sp3d hybrid orbital. Fourth one is also sp3d. And fifth one is also sp3d. So per hybrid orbital, we are having 20% s character plus 60% p character plus 20% d character per hybrid orbital. Per hybrid orbital. Now, how many electrons we have to fill over here now? Let's count them first. Here we are having 2 electrons in 5s and 3 electrons in 5p and 1 electron in 5d. So we are having total of 6 electrons. So let's fill that 6 electrons according to the Hund's rule in the hybrid orbitals. That's a redistribution of electrons. The first electron, second, third, fourth, fifth and the sixth. So we have redistributed the 6 electrons in the new hybrid orbitals. And on the other hand, we are left with 4 atomic orbitals of 5d. Here we are left with 4 atomic orbitals of 5d which are unhybridized. So let's let them mark also. So here these are the 4 unhybridized atomic orbitals of 5d where we have left our 2 electrons. I'm showing you that electrons. That electrons are, that's the first electron and second electron which are left in the unhybridized orbital. So let's fill them over here. That's the first electron in unhybridized orbital and that's the second electron on unhybridized d orbitals. Now let's talk about the side atoms. That's 2 oxygen and 2 fluorines. I'm talking about the fluorine first. That's our fluorine. What's the atomic number of fluorine? That's 9. Its configuration will be 2s2, 2p5. Let's make the 2p orbital. In p orbital, we are always having 3 degenerate orbitals. How many electrons we have to fill over here? The 5 electrons. So that's the first electron, second, third, fourth, and the fifth. So let's take this fluorine to the hybrid orbitals. I'm marking that's the 2p of first fluorine atom which is having 5 electrons. The first electron, second, third, fourth, fifth. Here we are left with 1 atomic orbital which is having 1 electron, which is going to have head-on overlap with the sp3d hybrid orbital of the xenon for the formation of sigma bond. So we got the first sigma bond which is sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of xenon with the p orbital containing 1 electron of fluorine. So now let's talk about the second fluorine atom. That's again 2p of second fluorine. That's again 2p of second fluorine which is having 5 electrons. So that's the first electron, second, third, fourth, fifth. Here also we are left with 1 atomic orbital of fluorine which is having 1 electron, which will have head-on overlap with sp3d hybrid orbital of xenon forming the sigma bond. So this sigma bond is again sp3d p because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of xenon with the p orbital containing 1 electron of fluorine. Now let's talk about the oxygen. Let's talk about the oxygen. The atomic number of oxygen is 8. So its configuration is 2s to 2p 4. Let's make the 2p orbital of oxygen. In this 2p orbital, we are having 4 electrons. The first electron, second electron, third electron, and the fourth electron. Here we are having 2 atomic orbitals which are having 1 more electron. So let's take it over here now. That's 2p of first oxygen. Now 2p is having 4 electrons. So that's the first electron, second, third, and the fourth. Here we are left with 2 atomic orbitals in oxygen which are having 1 electron each. So the first atomic orbital which is having 1 electron will have head-on overlap with the sp3d hybrid orbital of xenon forming the sigma bond. So we got this sigma bond That's sigma sp3d p, because this sigma bond has been found by head-on overlap of sp3d hybrid orbital of xenon with the p orbital of oxygen. Now, in this case, we are having, let me take a different color, one more atomic orbital of oxygen which is having one electron, and this atomic orbital of oxygen will have lateral or side overlap with the unhybridized orbital of xenon, forming the pi bond. So we got the pi bond which has been formed between the sidewise overlap of p orbital of oxygen and a d orbital of xenon, and this pi bond will be termed as p pi d pi bond, because this pi bond has been formed by lateral or sidewise overlap of p orbital of oxygen containing one electron with the unhybridized d orbital of xenon containing one electron. Now let's come to the second oxygen atom. The second oxygen atom is also having 2p, which is having 3 orbitals. So that's the 2p of second oxygen. And it's also again having 4 electrons, the first electron, second electron, third electron, and the fourth electron. So here we are again left with 2 atomic orbitals containing 1 electron each. Now, here the first atomic orbital of 2p, which is having 1 electron, will have head-on overlap with the sp3d orbital of xenon, forming the sigma bond. So this sigma bond is again sigma sp3d p, because this has been formed by head-on overlap of sp3d hybrid orbital of xenon with the p orbital of the oxygen. Now we are left with one atomic orbital of oxygen which is having 1 electron, and this orbital is going to have side or the lateral overlap with the unhybridized d orbital of xenon, forming the pi bond. So that pi bond will be p pi d pi. Why so? Because this pi bond has been formed by lateral or sidewise overlap of p orbital of oxygen with the unhybridized d orbital of xenon. That's why this pi bond has been named as p pi d pi. Now, one thing which we are left here, let me take some another color. Let us take this color. Here we are left with the 2 electrons in the first sp3d orbital. The 2 electrons in the first sp3d orbitals will be termed as lone pair of electrons. So now, that's all about the hybridization we have got, in which I have shown you that the 2 fluorine atoms are forming sigma bond with the hybrid orbitals of xenon. The 2 oxygen atoms are also forming 2 sigma bonds with the sp3d hybrid orbitals of xenon, and both of the oxygen are also forming pi bond with the unhybridized d orbitals of the xenon by the lateral or the sidewise overlap. So now, let's talk about the structure. We got the hybridization to be sp3d. The standard structure for sp3d hybridization is trigonal bipyramidal. That's trigonal bipyramidal. Now let's arrange the lone pairs and the pi bonds in the trigonal bipyramidal structure. Our central atom is xenon. The lone pair will always occupy the equatorial position. That's the lone pair. Now, the pi bonds will also occupy the equatorial position, and pi bonds are formed by oxygen atom. So I have taken one oxygen atom on the one equatorial position and the second oxygen atom on the second equatorial position. Now, let's link them imaginarily to make you understand the structure in 3 dimensions. I'm just making you understand the structure in 3 dimensions. These dashed lines are not the bonds. It's just an imaginary linkage. Now we are left with 2 fluorine atoms. The both of the fluorine atoms will occupy the axial position. So that's the axial positions. So while naming the structure, we have to ignore the lone pair. So this structure will not be called as trigonal pyramidal. This structure will be called as seesaw. The name of this structure is seesaw structure. Now, let me label the diagram also. The sigma bond of fluorine is called sigma sp3d p, because this has been found by head-on overlap of sp3d hybrid orbital of xenon with the p orbital of fluorine. The sigma bond of another fluorine is also sigma sp3d p. Now, the sigma bond of oxygen is also sigma sp3d p. Sorry, that's sigma sp3d p. And the sigma bond of another oxygen atom is also sigma sp3d p. We are left with pi bonds, and these pi bonds are termed as p pi d pi bonds, because this pi bond has been formed by sidewise or lateral overlap of p orbital of oxygen and the d orbital of xenon, the unhybridized d orbital of xenon, and the another pi bond is also p pi d pi. So let's re-revise the hybridization. Please come back to the structure. Here the first fluorine atom, the one atomic orbital of fluorine is having head-on overlap with the sp3d hybrid orbital of xenon, forming the sigma bond, that's sigma sp3dp. The second fluorine, in case of second fluorine atom, again the one of the p orbital containing one electron is having the head-on overlap with the sp3d hybrid orbital of xenon, forming the sigma bond, that's sigma sp3dp. Now let's come to the first oxygen atom. In case of oxygen, we are having two atomic orbitals in 2p which are having one electron. Out of that, one atomic orbital of 2p of oxygen is going to have head-on overlap with the sp3d orbital of xenon, forming the sigma bond, and the another atomic orbital which is having one electron is going to have sidewise or lateral overlap with the unhybridized d orbital of xenon, forming the pi bond, that's p pi d pi. Now let's come to the second oxygen also. In this case also we are having two atomic orbitals in oxygen which are having one electron. Out of that, one atomic orbital is going to have head-on overlap with the sp3d hybrid orbital of xenon, forming the sigma bond, that's sigma sp3dp, and the another atomic orbital of 2p having one electron is going to have sidewise or lateral overlap with the unhybridized d orbital of xenon, forming the pi bond, that's p pi d pi. Now that's all about the hybridization. Let's come to the energy points. Now I'm talking about the energy points. Here two types of energies are consumed. That's the promotional energy. The promotion of 3 electrons from 5p to 5d will consume energy. So here is the consumption of promotional energy. Here is the consumption of promotional energy. Now, another endothermic process is the intermixing of atomic orbitals. That's the hybridization process. So at this point, here is the consumption. Here is the consumption of hybridization energy. Here is the consumption of hybridization energy. Now, at last, Here the formation of 4 sigma bonds and 2 pi bonds, which will release energy. So I'm writing the energy is released. The energy is released during the formation of 4 new sigma bonds and 2 new pi bonds, which compensates the promotional energy, and hybridization energy, as both of the endothermic processes, that's promotional energy and hybridization energy, is compensated during the formation of 4 new sigma bonds between the hybrid orbital of xenon and the p orbitals of fluorine and the oxygen, and the 2 pi bonds between the d orbitals, the unhybridized d orbital of xenon and the p orbitals of the oxygen. So both the endothermic processes are compensated during the formation of 4 new sigma bonds and the 2 pi bonds. That's why the formation of XeO2F2, xenon dioxy difluoride, is chemically feasible or practically possible. I'm repeating it again. The two endothermic processes, the promotional energy and the hybridization energy, is compensated during the formation of 4 new sigma bonds between the sp3d hybrid orbitals of xenon and the p orbitals of fluorine, and the 2 new pi bonds, that's between the p orbitals of oxygen and the unhybridized d orbital of xenon. That's why the formation of XeO2F2, the xenon dioxy difluoride, is chemically possible and practically feasible. So that's all for today's lecture. I hope you all understood sp3d hybridization with 1 lone pair and 2 pi bonds in the main structure with an example of xenon dioxide difluoride. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students.